Snow is surprisingly hot, and this heat can kill. Avalanches kill about 150 people every year. But one of the biggest mysteries is how the shape of a tiny snowflake can cause something as deadly and powerful as an avalanche. Okay, it might sound unbelievable, but let's start from the beginning. You might imagine a typical snowflake like this, but there are actually over 35 different types of snowflakes. As a snowflake falls, it can change its shape and size multiple times. And all this is possible because snow exists almost always near its melting temperature. What does that mean? Well, it means it's considered a hot material, so it's always undergoing some kind of phase change, like from solid to liquid, solid to vapor, or liquid to vapor. So what's this got to do with avalanches? Well, all these changes to the shape of a snowflake mean it can become much more dangerous once it hits the ground.
So when we look out at the snow, it seems like it's just a uniform blanket, but that's not the case. If we look inside the snowpack, we see that it's formed of many discrete layers. We might see some layers that look like those beautiful snowflakes that fall out of the sky. Other layers might be small and rounded and well bonded. And then we might have some weak layers that tend to be large angular grains that are pretty loose.
And that's the thing. The shape of a snowflake or a crystal can make a layer either strong or weak. And the most dangerous avalanches have this weak layer. One way to imagine it is like a row of wine glasses, all stacked on top of each other. They might be relatively stable by themselves, but as the layer of snow above gets thicker and thicker, as dense as a row of bricks being stacked on top of the glass, eventually that weak layer will break. This is when we get the avalanche. Of course, there are a few other ingredients that contribute. The angle of the slope is important. About 39 degrees is the avalanche sweet spot. A thick layer of snow on top. And also, we need some type of trigger. And usually, that's us. Regular humans who trigger 90% of all avalanche disasters. But still, the most important ingredient of all is that invisible weak layer, the hidden killer below the surface.
Avalanche workers are tracking weak layers throughout the season, and if an avalanche occurs, the first question you're always asking the other avalanche worker is, which weak layer did it run on, and how deep was that weak layer buried?
So what is it that creates these deadly weak layers? It's heat.
So weak layers form in the snowpack due to temperature gradients, and oftentimes large temperature gradients are present in the snow because the ground surface is almost always near 0 degrees C, whereas the air temperature above at the top of the snowpack can be significantly colder than that.
Those temperature differences cause the movement of water vapor, and as it moves, it forms these large angular crystals that don't bond easily to each other, and therefore become weak layers. So there are three main types of weak layer that cause the most concern for avalanche experts: depth hoar, surface hoar, and near surface facets. First on the list is depth hoar, or sugar snow. Its snow grains grow like inverted cups that are stacked up on top of each other.
You can almost see them just with your naked eye. You put your hand into the snow pit wall and it just comes pouring out like sugar, and you have these big sparkly grains.
And this is a type of weak layer that's responsible for most of the avalanche fatalities.
Depth hoar forms at the ground snow interface. Generally means that the entire snowpack is engaged in the avalanche.
Surface hoar is the pretty one, and you might even recognize this one.
The conditions that form surface hoar are the same sorts of conditions that put frost on your car windshield. So if you find yourself in the morning scraping the frost off of your car windshield with your scraper, you probably could find surface hoar on the snowpack.
These snow grains look like bird feathers sticking up out of the snow surface. The problem is that when we have all these crystals lined up, it resembles a house of cards, and it acts like one too. So when more and more weight piles on top, the house of cards collapses, and there's an avalanche. The final one is near surface facets, aka recycle powder or loud powder.
Because it tends to be very fun to ski, you almost sound like you're skiing through little crystals because you can hear the snow breaking.
But that breaking is also what can make it dangerous. These are small angular crystals of about 1 millimeter in size, and they tend not to bond well with crystals around them. That's why they're loose and sugary, and also why they form weak layers. So that's why understanding more about these weak layers is at the cutting edge of avalanche science. It all comes down to the strange properties of these beautiful, delicate little snowflakes, and how their shape can be formed and morphed by the heat around them.
Could a large enough earthquake split the Earth in two? We all know earthquakes can wreak havoc. This is what a 9.1 to 9.3 magnitude earthquake looks like. It's from the Sumatra Andaman earthquake in 2004, the largest earthquake in the 21st century and the third largest recorded of all time. It caused tsunamis up to 30 meters high across the Indian Ocean and triggered further earthquakes as far away as Alaska, and Alaska's pretty far away. So if this is what a magnitude 9 earthquake looks like, what would it take to split the Earth in two? And could it ever happen? Let's take a step back. What does magnitude even mean? Well, there are actually lots of different scales used to measure earthquakes, but the most widely used these days is known as the moment magnitude scale. It measures the power of an earthquake both in terms of the amount it shakes the ground, but also the amount of energy released. There are actually millions of earthquakes a year, but the majority are at the lower end of the magnitude scale.
Those ones are not always large enough to be felt. Normally, the largest earthquakes are the ones that we see in the news. So, for example, magnitude 7 and above earthquakes, we tend to have around 15 of those around the world per year.
But why does the severity of earthquakes seem to increase so dramatically as we enter those higher magnitude numbers?
So the moment magnitude scale is logarithmic, and what this means is that for every unit of magnitude you go up, the amount of ground shaking increases by a factor of 10.
So a magnitude 10 earthquake is not just double the power of a magnitude 5, it would actually be 100,000 times more powerful and release more than 33 million times more energy. So the numbers can get really big, really fast. Almost all earthquakes are caused by clashes between the huge tectonic plates that have been shifting all over the planet for 3 billion years. As they move, they sometimes lock together along a so-called fault line, causing a huge buildup of energy, until suddenly, they slip. And that's the earthquake. So the longer the fault line, the more friction and energy gets built up. And the longest faults of all are in what's called subduction zones, where an oceanic plate is forced under a continental plate. This creates what's known as a megathrust earthquake.
As a result of the amount of area available to rupture along these megathrust faults, that means the subduction zones create some of the world's largest earthquakes.
And almost all subduction zones on Earth are found around the Pacific Ocean. It's called the Ring of Fire. And it's home to 75% of the world's volcanoes and 90% of the Earth's earthquakes. With the largest fault lines in the world, if ever there was going to be an earthquake capable of splitting the Earth, it would be here. So how big a quake would it take to split the planet in two?
So we know the radius of the Earth is 6,300 kilometers. So then if we want to split the Earth fully into two, then we're looking at a diameter of about 13,000 kilometers. So if we take a fault length of about 13,000 kilometers and maybe take an assumption of a fault width of 1,000 meters and say that fault moves 50 meters during that earthquake, that's going to be theoretically a magnitude 10.8 earthquake.
That sounds scarily close to the magnitude 9s we've seen already. So how likely is a magnitude 10.8 earthquake?
Okay, so to produce a magnitude 10 earthquake, we would need a single fault that ruptures that would be long enough to extend around most of the planet. So for a magnitude 9 earthquake, we need about 1,000 kilometers long fault. And then to be able to produce a magnitude 10, we need to increase that by a factor of 10 again. So we'd need around a 10,000 kilometer long portion of fault. And to our knowledge, no single portion of fault exists that could produce such a large earthquake.
The longest fault we know about for now is 5,500 kilometers, the Sunda megathrust. That makes a magnitude 10 earthquake extremely unlikely. This means that the Earth itself would never be able to generate enough seismic energy to split open, unless we had some sort of massive asteroid impact. But that's another film. What we really need is a way to know if and when the big quakes are coming.
Ultimately, we want to be able to predict earthquakes. That would be great, to know exactly when and where they will occur in the future. The Earth is just too complex, and there's a degree of sort of chaos and randomness in the system that we just can't model. What we can do, though, is to issue earthquake forecasts. So a lot like a weather forecast, we are given a certain probability of an earthquake happening in a given region in a given time frame.
Could a hypercane end all life on Earth? Wait, what's a hypercane? Well, a hypercane is like a hurricane, on steroids. With wind speeds of over 800 km per hour and a duration of several weeks, a hypercane could be large enough to cover the whole of North America, while also reaching 40 km high into the Earth's upper stratosphere. It's pretty safe to say this would cause global devastation, and it was first proposed by Professor Kerry Emanuel.
Well, hyper, of course, means something that's fantastically out of bounds, and the cane comes from hurricane.
So a hypercane is an extreme tropical cyclone that forms if the sea surface temperature rises above 50 degrees. And it's terrifyingly huge. Professor Emanuel believes it may actually have happened once before, potentially having contributed to the mass extinction of the dinosaurs. But before we get too carried away, luckily for us, hypercanes are just theoretical, at least for now.
Well, I coined that term back in the 1980s when I was working on a theory that governs the maximum intensity, the maximum wind speed you can have in a hurricane.
But there was an anomaly that just kept coming up.
If you tried to push the temperature of the ocean too high, you couldn't solve the equations. They didn't have a solution. And it was very puzzling to me.
So Professor Emanuel had to come up with an entirely new theory, the hypercane.
Well, hypercanes would form if the ocean temperature became extraordinarily large, particularly if it did so in a small region, a few hundred kilometers across. By large, I mean in excess of 50 degrees centigrade.
The reason the temperature matters so much is because hurricanes form above warm oceans, when hot air rises and cold air comes rushing in to replace it, creating a spiralling and growing storm cloud. The hotter the seas, the greater the cloud. Okay, so the largest recorded tropical storm is Typhoon Tip, a typhoon that emerged in 1979 and affected multiple countries. The storm reached peak sustained wind speeds of 305 km per hour, with a wind diameter of 2,220 kilometers. That's big enough to cover around half of the United States. Oh, quickly since we're here. If you're wondering what the difference is between hurricanes, typhoons and cyclones, it turns out nothing. At least nothing scientifically. All three words describe the same weather system, a tropical storm, and the difference is as simple as which part of the world the storms form over. Back to the hypercane. Will we see another one of them anytime soon? Well, there's no doubt sea temperatures are rising and making hurricanes more powerful.
Well, so in today's climate, hurricane wind speeds at the surface can get up to maybe close to 90 meters per second. And we expect that to go up as we continue to warm the climate. And in fact, we're beginning to see evidence in observations that it is going up. So maybe we'll have a 95 meter per second hurricane or 100 meter per second. And because the destructive potential of windstorms goes up very quickly with wind, at least as the cube of the wind, that 3 or 4 meters per second is actually a lot, makes storms potentially a lot more damaging. So this is something to watch.
If ocean temperatures did continue to rise above 50 degrees C, there's no doubt hypercanes would cause devastation on the ground. But higher up, there'd be a potentially even more damaging consequence, because a hypercane would reach so high that it would actually interact with the ozone layer.
And one of the things that interested us about the computer models of the hypercane is hypercanes were pumping up all kinds of material into the middle stratosphere, like water vapor, that really don't belong there. Would, through a series of chemical reactions, lead to the destruction of ozone, which would endanger life on the surface. And we pose that as a potential link between bolide impacts and mass extinctions that are thought to have gone along with them. Hypercanes could be an explanation for the extinction of the dinosaurs.
Without the ozone layer's protection, and with continuing or even multiplying storms, life would struggle to survive on the surface. It really could lead to the end of life on Earth as we know it. So here's the big question. How likely is all this? It's impossible to have missed the fact that global sea temperatures are rising. But luckily, we are a long way from 50-degree sea temperatures and any resulting hypercanes at the moment. The Indian Ocean is the warmest, and even that only has a sea surface temperature of around 30 degrees C in places. I think it's time for some good news.
In today's climate, the warmest ocean temperatures we see in the tropics, we expect that they will continue to go up, maybe to 32 or 33 degrees, but not to 50 degrees. In fact, we don't think that's really happened even in the Earth's past. It's not something that will happen as a result of natural or even man-made climate change. It's not something to worry about.
So without any asteroid-induced world-changing events, we're unlikely to ever see a hypercane, as fascinating as the name and theory may be. But perhaps the dinosaurs weren't so lucky. The Earth's core is as hot as the surface of the Sun. That's around 6,000 degrees Celsius, hot enough at normal pressures to melt all known materials, even the one with the highest melting point, tantalum hafnium carbide. Luckily, the total diameter of the Earth is 12,742 kilometers, which means that you're protected from the core's heat by around 6,000 kilometers of rock beneath your feet. So then how do we know how hot it is down there? We could try digging, and the furthest anyone's ever dug down is a project called the Kola Super Deep Borehole in Russia. It started, like many things from the era, as a part of the Cold War race with America. But many other countries have also had a go. In the 60s, America tried drilling into the Pacific Ocean floor, then the German Continental Deep Drilling Program overtook them. And as recently as 2007, a Japanese drill ship got the furthest through the ocean floor. But the Russians have still made it the furthest overall. They reached 12 kilometers down. That's deep enough to fit 14 Burj Khalifas end to end, and you still wouldn't be touching the bottom. Pretty impressive. But 10 kilometers down, the temperatures started to get unexpectedly high.
As you dig deeper and deeper and deeper into the crust, it does get hotter.
At 12 kilometers down, the rock was 180 degrees C, and drilling had to stop.
The key thing really is having an engineering infrastructure that can withstand those temperatures and not fail or melt as it gets hotter.
While it's an impressive feat of engineering to get that far down, 12 kilometers isn't even halfway through the Earth's outer layer, the crust. If we're barely able to make a dent in the crust, how do we know how hot it is in the middle? Well, in 2013, scientists measured the way seismic waves from earthquakes travel through the Earth. Think of it like a planet-sized ultrasound. From this data, we know that the Earth's core is actually split into two parts, an outer core of liquid iron and nickel, and a solid inner core at the very centre. Experiments show that the only way this is possible is if the solid inner core is as hot as 6,000 degrees Celsius. That's as hot as the surface of the Sun. And the mind-blowing thing is that the pressure is so intense at the inner core that the solid iron and nickel literally can't change state, even though the temperature is way past iron's boiling point, and you or I might expect it to be a liquid. The big question is, why? How did it get so hot down there?
So our planet was formed about 4.6 billion years ago. And it started off as this kind of homogeneous mass of molten rock, where rock debris and material that was floating around accreted together. And as this mass got larger and larger as it grew, its gravitational force grew as well. Alongside that, there's a lot of radioactive decay happening. We have these metallic elements that are always decaying away, and that creates heat. This process just escalated in these really dramatic proportions.
As the planet got hotter due to the radioactive decay, all of the heavy elements like iron sunk towards the centre, creating even more heat and the hugely hot iron core we still have to this day. This means that the Earth's core is actually younger than the Earth itself, having formed more recently, and its heat is also responsible for life as we know it.
What's really key about our core is that it actually creates the magnetic field. As heat moves from the inner core into the outer core, it's swirling about, it's swishing about. It's this movement that's going on within the outer core from this liquid iron that then creates the magnetic field or the magnetosphere, that which is really important for life on Earth. It protects us from solar radiation, from solar winds and particles, which are really, really harmful to life on Earth.
So we're far enough away from the core that we're not going to spontaneously combust anytime soon. But more than that, this enormously hot core is actually the reason we're all here today.
Knowing this process, this powerhouse, this heart, is underneath our feet every single day, pumping away, it makes you stop and realize, oh my goodness, this planet, it's alive.
So, the Earth isn't actually round. And Mount Everest is not the highest point on the planet.
Okay, let's break this down. We're used to seeing images of the Earth as a perfectly rounded sphere, like this, or this, or this. But that's wrong. Before you say it, no, it's not flat either. While we had a few interesting guesses in the beginning, we've actually known the Earth isn't flat since around the 5th century BC, thanks to ancient Greek philosophers and mathematicians.
But it wasn't until around 1200 years later that Sir Isaac Newton first exclaimed that the Earth is not perfectly round. It's actually what's called an oblate spheroid.
The best way to describe it is as a rugby football, the short axis being the rotation axis about which the Earth spins, and the long axis lying in the equatorial plane.
And it turns out there's a big difference between round and round-ish. If you measured the Earth's diameter from the North to the South Pole, you'd actually get a different number compared to measuring the diameter around the equator. A difference of just over 42 kilometers. The equator is bulging outwards.
That means that a person standing on the equator is about 20 kilometers closer to the moon than someone at the North Pole.
Which makes the equator very good for stargazing.
Okay, in the grand scheme of things, that's not a huge difference. But it is enough to ensure that Everest is not actually the highest point on Earth. There's a reason you probably thought that Everest was the highest mountain on Earth, but that's only because typically we measure mountains from sea level. And if you measure from the absolute centre of the Earth instead, then Everest is no longer in first place. That prize goes to Mount Chimborazo in Ecuador, and Everest isn't even in the top 3, it's 10th. Mount Chimborazo gets a massive height boost from the Earth's imperfect shape, thanks to being only about 1 degree from the equator. This means it's more than 2,000 meters further away from the center of the Earth than Everest. So why is the Earth this shape? Well, the main reason for this not exactly round shape is because of the Earth's rotation. The planet's constant spinning makes it bulge at the equator, thanks to a centrifugal force that pushes outwards at the center when an object spins, and that force is bigger at the equator than at the poles.
We can measure the shape of the Earth, we can measure its gravity field thanks to satellite technology. The satellite's orbit is determined in the first instance by the attraction of the Earth on that satellite. So if we can track a satellite precisely, what we will see is that its orbit isn't a nice elliptical, but you'll see little wiggles on it.
The imperfect orbit of satellites tells us a lot about the imperfect surface below.
It tells you that somewhere underneath that satellite at that time, there's a density anomaly, that there's either an excess of mass or a deficit of mass compared to our ideal shape.
This shows us that while Earth is certainly not a perfect sphere, it's also not a perfect oblate spheroid either. The peaks of mountains and volcanoes and the troughs of craters and canyons all play into the shape of the Earth. But even accounting for that, keeping on top of the true shape of the Earth is trickier than it might seem, and that's because it's not a fixed shape.
It's changing its shape all the time on different time scales and by different amounts. But on the short time scale, a good example is every 12 hours the ocean tides repeat themselves. These tides are associated with redistributions of mass, and the shape of the Earth changes accordingly by something like 20 centimeters, for example.
That means it's not just the tides that go up and down, but also the ground you're standing on now. And understanding how much and how often it changes shape is integral to, well, just about the entire modern world. From weather tracking to time zones to maps and GPS itself.
And now that system, because there are so many satellites up there, so you had this great surfeit of observations. So from these, you could determine your positions in real time effectively. And nowadays we can do that at sort of centimeter accuracy.
Our planet acts like a living organism, dynamically moving and changing in both the short and long term. We've come a long way since we first called the Earth round. Now we can scientifically say it's round-ish.